Sir, yes, sir.
Yeah.
We have started recording, sir.
Yeah. Good afternoon to everyone. I welcome all of you to the 18th lecture in the lecture series in Nonlinear Dynamics. I'm happy to introduce today's speaker, Professor Pragya Shukla, to you. Professor Pragya is a well-known person to our department. She has visited few times our department, presented seminars, and interacted with the members of this department. We are lucky to hear Professor Pragya's lecture one more time today. I'm also happy to see Professor Sir Michael Berry is also participating today's lectures. I welcome you, sir, to the lecture series. In view of our MSc students, I wish to read out Professor Pragya's biodata in a brief manner. Professor Pragya did her MSc in IIT Kanpur and completed her PhD in Jawaharlal Nehru University in New Delhi, and then she did her postdoctoral research at Theoretical Physics Division, Saclay, France, and spent some time in Germany before returning to India. During her academic career, Professor Pragya had won several awards starting from her school days. Several students have completed PhD under her guidance. As far as research is concerned, Professor Shukla is working on several problems, mainly on the following four directions, namely studies on system-dependent random matrix ensembles, to weak measurements and low temperature properties of glasses and physical Curl forces. Today, Professor Shukla is going to talk about physical Curl forces. I think she is concentrating in this particular problem for the past 5 years or so with Professor Sir Michael Berry. Students, if you want to know more about Professor Shukla's publications and academic endeavors, please visit her homepage. Now I hand over the session to this Professor Shukla. Over to you, Professor.
Yeah, okay. Thank you very much for the very kind invitation to present my work with Professor Michael Berry to students of great university, where many important ideas on nonlinear dynamics have come out under the leadership of Professor Lakshmanan. And actually, I feel it is I'm honored to be speaking to students of this great university. And let me not talk much about it now. So, because I know the topic I have chosen is especially for dismiss. Cannot share my screen additionally. You're sharing another application under. Wait. A window. Let me try. Allow. Can you see my screen? Yeah.
Yes, it's coming. Yes.
Ignore.
Good.
Okay. So so it's a privilege on my side actually to speak to these very bright students. And the topic which I have chosen, there is a particular reason. Not only that, first of all, because it's a very fundamental topic, and we have started thinking about this topic for last few years only, and during last 10 years probably. And because I work on several other directions, and Professor Berry also works on several other directions, we are actually looking forward for some young, bright student to take up these problems, because it seems there is a lot of potential. And the nonlinear dynamics and students of Trichy is the right forum to introduce this problem to, because the students under the guidance of Professor Lakshmanan and all others, his students and who are now professors there, you have all guided your students such strong. They have such strong inclinations in these differential equations, non-linear dynamics, and all these kind of aspects, that they are the right people to hear about it and think about it more, and really enlighten us more about this topic. So, with not saying more, thinking that you are all MSc students, I will try to go very slow. And let me now start. This is something, as you will find, is very basic. And let me now go. Okay. So basically what I'm going to talk about is the Newtonian physics. Okay. We all start with physics, but the first time we start physics, we hear about Newton's laws. So I thought that let's start with Newton's laws. So this is the, as you see, R is the position vector and double dot is the second differential, and R double dot is F of R, where F is a force. So I'm considering a force acting which only depends on the position. Okay, this is the title of the talk today. But before that, let me discuss a little bit about, remind you about the conservative versus non-conservative forces. And when we talk about conservative versus non-conservative forces in this lecture, we are going to talk about conservative forces in the position space. Okay. For example, work done along a closed path. So if the work done along a closed path is 0, then it is a conservative force. The work is done by a conservative force, and if his work is not 0 along a closed path, it is a non-conservative force. Okay, for example, I have written it here again. Conservative forces, if you go between 2 points A and B along any path, for example, path this one, or path this one, or this path, the work is equal. And work path independent can also be seen in another way, is that the force with which this work is done, the curl of that force is 0. Okay. Now, if a curl of a vector is 0, probably most of you remember, that means it can always be written in a gradient form. The force can always be written in a gradient form, because curl of a gradient field is always 0. So that means for any force for which the work is path independent, that kind of force can be derived from a potential. And if you can write, that means a scalar potential. Then therefore a Hamiltonian formulation is possible, because Hamiltonian can be written as a sum of kinetic energy and potential energy. However, if the force is non-conservative, by that I mean if the work done along 2 points AB in the position space is not equal, W1, which is work done along this line, is not same as the work done along this line. And this, so work is not only position dependent, that means A and B, it is also the path dependent. In that case, if you remember your basics of graduate level, PSc level, then you know that then, because work can be written as F dot dl, and F dot dl by using integral theorem, you can write F dot dl as del cross F ds, and then you can write del cross F is not equal to 0 if it is not work is not preserved along a closed circle. And in that case, if del cross F is not 0, so that means F cannot be written in a gradient form. So that means no standard Hamiltonian formulation is possible. So if you do not remember your basics, students, then just remember that for non-conservative forces, no standard Hamiltonian formulation is possible. The non-conservative forces satisfy this condition that del cross F is not 0, and F cannot be written as a scalar potential in general. Besides this was the case in the position space. Now let us go to the usual representation. We know that when we talk about Hamiltonian formulation, we immediately start talking about phase space. Okay, so if Hamiltonian exists, then you know Liouville equation in phase space, where rho is the density, how the density of points, phase space points, and phase space coordinates depend both on position as well as momentum. So how that changes with respect to how does that change? What is the continuity equation for the density of points in the phase space? So you know this Liouville equation, that this is, if rho is the density of points in the phase space, and r dot is the position velocity, and p dot is the momentum, actually the acceleration, momentum derivative with respect to time, and r dot is a position derivative with respect to time, then this is the continuity equation. However, if there is no Hamiltonian, so naturally you cannot discuss about the phase space formulation. And then we think about the state space, the Newtonian space. And then you have that del rho by del t, instead of this part of the equation remains same. However, instead of p dot, now you have v dot. Okay, v is the velocity. And so if Hamiltonian exists, this is the Liouville equation. If no Hamiltonian, this is the Liouville equation. However, if particle density is constant, if rho is constant, that means no source, no sink, then in the case of Hamiltonian formulation, this term is equal to 0. In the case of no Hamiltonian formulation, this term is equal to 0, but they both have the similar kind of formulation. Instead of only difference is this derivative with respect to s. In one case, s is p. In the other case, s is v. But this is also called the volume preservation. So in the case of no Hamiltonian, the volume is preserved in state space. In the other case, volume is preserved in phase space. So now let me sum up what I have told you so far. This seems to suggest there are various possibilities. One condition we have in the dynamics, what is happening in the position space, other is what is happening in the phase space or state space. And the combination of the two can lead to various possibilities. Conservation in position space can conspire with volume preservation in state or phase space in 3 possible ways. There are 4 possible ways, of course, but the 4th is very well known, and that's why I am not going to mention it. First is, of course, the well-known conservative non-dissipative forces. Conservative, that means the work done along a closed circle is 0. Non-dissipative, that means volume is preserved. The conditions are represented by this form, del r cross f is equal to 0, and this condition, this is a volume preservation condition. Then the second condition is both of them are non-zero. Okay, so that means non-conservative as well as dissipative forces. Okay, this is of course another category and not yet really studied in great detail. Of course, actually this is the part of the or rather very well known. I don't know which category I should put it in. Okay, so but the third one is the one which I'm going to focus on in this talk, and that is when del cross f is not equal to 0. However, the volume is preserved. That means this condition is satisfied. Okay, so because these forces, the curl of these forces is not 0, and therefore I refer them as the curl forces. Now, the kind of forces which I am going to talk about in this talk, because f in general can be a function of both position and velocity, but we are mainly interested in, for reasons I'll tell you probably in the end, we are mainly interested in only forces which are position dependent. Okay, so not the velocity dependent, because those kind of forces are already known, whose curl is not 0. So now the novelty is about the forces whose curl is not 0, but they are only position dependent and they preserve the volume. That is the topic of this talk. Now, why we are so keen about studying these kind of forces more, these kind of curl forces which I just described here, is because first of all, there is a fundamental interest that the Noether's theorem does not apply. Now, what is the Noether's theorem? So let me just indicate to you. Noether's theorem states a continuous symmetry of a physical system implies that some physical properties conserved. Okay, so there is, for every symmetry, there is a corresponding conserved physical property, and vice versa. Each conserved quantity has a corresponding symmetry. For example, if I simplify more, the spherical symmetry corresponds to conservation of angular momentum. Translational symmetry implies conservation of the linear momentum. However, in case of the curl forces, it so happens that curl forces break the link between symmetries and conservation laws. Let me explain it to you by an example. Consider the curl forces in 2 dimensions. A tangential force that means acting along the angular direction, angle. This is the acting along, this is the origin. This is the distance of the particle from the origin, and the force is acting along the direction of the angle. So the magnitude depends on the position, but the direction of the force is along the angle. Now you take the curl of this force, because curl of this force is, no, not, first of all, not curl. You don't have to take the curl of this force, first of all. Just take the torque of this force. What will be the torque? Torque will be R cross FR, and because the R cross theta will give you, I mean, because this is cos 90 degree, and therefore you will get the torque is RFR. Okay, so torque is not zero, but however there is a symmetry. So although the force is rotationally symmetric, because the magnitude does not depend on theta, but torque is not zero. So what does it mean? That angular momentum is not conserved. So force is rotationally symmetric, but angular momentum is not conserved. So this is symmetry without a conservation law. Okay. Now, okay, I can, while I'm at it, let me just say there I could have given you a counter example that not all rotationally tangential force of this form need to be curl forces. So this is a special aspect of the curl forces, but need not all these forces need not be, not all rotational tangential forces are always curl forces. So you should be careful before applying this. Now let me give you another example, that consider a radial force dependent on radial distance and angle. Now magnitude depends on both distance as well as angle, and the force is acting along the radial direction. So what happens? This is the magnitude of the force, and this is the angle. Now you calculate R cross FR, the torque, and now R cross R gives you 0, and therefore the torque is 0. However, the force is not rotationally symmetric. So although there is no symmetry, rotational symmetry in the dynamics, but there is no spherical symmetry, but there is a not a spherical symmetry, I should have said rotational symmetry, but angular momentum is conserved because there is no torque. So there is a conservation law without symmetry. So that means when you talk about these kind of forces, it is possible. Because I have not, why I am saying it is possible, because I haven't yet taken the curl of these forces. So I do not know whether these are curl forces or not, because I have not defined G. Because the curl is 0 or not 0 will depend on what is G or what was F in the previous formulation, previous example. So that means I've just given you how the Noether's theorem can be violated, and what actually Noether's theorem means. That means there can be conservation without symmetry or symmetry without conservation laws in force fields. Okay. Now let me come directly to the curl forces and take a special case, again rotational tangential force, F of R, F, where the magnitude depends only on the position, and this is acts on the angular direction. Now this I have specially chosen, I'm giving more detail. Usually in my talk I do not give so many details, but I'm giving this detail basically keeping the Trichy school in mind, because I know you have such strong department of nonlinear differential equations and all that. Therefore I have deliberately chosen this slide to keep. Okay, so actually you can write it, because the radial force is 0. There is no component, it is the only angular component, there is no force in the radial direction. So you can write down the acceleration. Acceleration turns out to be this form. Now the typical definition of the angular momentum J, R squared theta dot. Now you consider its evolution. So the rate of change of momentum, angular momentum, is given by the torque, and torque you can calculate from here, R cross F, because R cross theta will give you RFR. So this is the angular momentum. And the question is, now you solve this equation and Srivida, because this is now the Newton's law kind of equation. You solve this equation and work out the dynamics of this system. Okay. And we are assuming, of course, here that del cross F here is not zero. Okay. So we are assuming here that del cross F is not zero here. Okay. So now what happens that how do you solve this equation? And therefore, I am giving you the best way is to one easy way. And actually, it's a very illuminating way. And that's why I'm talking about it. That you do the separation of variables. Because why separation of variables? Because this side depends only on R, the left hand side depends on T, and therefore it is possible to apply the separation of variables. You define a new radial variable Y in this form. Let's not get into detail. You can always look at my slides later on, but let me just flash these ideas to you. That you define a new variable and a new radial variable as well as new independent time variable, but new independent time variable should be chosen as J. J was your original angular momentum. When you use this new Y and new J, you can exactly prove that dy by dj, which I give a new name Y prime, is equal to R dot. What was R dot? R dot was dr by dt, where it was the original velocity. Okay. So dy by dj is equal to R dot. Now you differentiate it. Y double prime. The prime here corresponds to derivative with respect to j, the new time variable. So d2y by dj square can be written exactly in this form by using, because when you will differentiate it, dr dot by dj and then dr dot by dt, dt by dj, and dt by dj is given by 1 by r by fr. So when you will substitute all that, you can easily see, just take a pen and paper and you can work it out, that d2y by dj square can exactly be written in this form. The question is, if you can solve this equation, then you get y of j by solving, because this side depends on j, and for a given r, you can solve it this, and then from y of j you can get r by j, r of j, and from there you can work out the time t of j by inverting it this, and from there you can work out the angle theta. These are standard equations, and therefore you can work it out yourself. That's why I'm not spending much time just mentioning it. So basically the idea is, if you can work out y of j, because y depends on r and j depends on r and t, so from there you can invert this and you can work out the angle dependence theta of t, which was the main variable of the dynamics. Okay. So now you consider a specific case, f of r is equal to r mu. Now those interested, they can quickly check that for that del cross f is not zero. Okay, so we are now considering a specific case, f of r is equal to r mu, because it is always good to start with simple cases. Okay, so and mu can be arbitrary power. So if you substitute it in this equation, so it turns out to be that y2 prime j becomes j square r4 plus mu. Okay, yeah, and then you can solve it. It turns out to be of this form. You can easily solve it, and it turns out to be of this form. Actually, in general, you can also see that instead of looking at this equation, actually why you look at this, that y evolution actually satisfies what is well-known equation, Hamilton-Fowler equation, and this is a very celebrated equation. I don't have to tell you because your department knows it much better than I do. That y2 prime j, when you substitute it here, it becomes of the, because here I was talking about j square only, r to the power f of r, and this is the more generalized form of Hamilton-Fowler equation. So this equation, what I'm talking about, corresponds to n is equal to 2 of the Hamilton-Fowler equation, and m is also a specific value. Okay, and A is also of specific value. So question is, what I am trying to say, if I have gone very fast and I have not been very clear, then all that I am trying to say is that if you start with this kind of force, rotational tangential force, and idea is to study the dynamics of the particle under this force field, because this force field is whose curl is not zero. Question is what new kind of dynamics it takes place. So all that is that you can map this problem to the well-known problem of solving Embden-Fowler equation. Okay, and a specific case of Embden-Fowler equation, and that specific case is given in this by these parameters. Now, your department people, Professor Lakshmanan and others in your department can easily tell you, and Professor Lakshmanan has written papers on Embden-Fowler equation. I have come, well, while I was working on it, I looked at his papers, and so I do know that it's, you don't know the solutions for all in general. Okay, only for very few cases, you know. General solutions are not known, but particular solutions are you can give. So one particular solution is of this form. So what I'm trying to say that in the curl force field, this Embden-Fowler equation very interestingly appears, and you have to work it out, and it leads to a lot of very interesting dynamics, because there are so many components of this curl force problem that I will not get into much more detail, but you can find a lot of, we have studied the dynamics for specific mu's, mu is equal to 1, mu is equal to -1, mu is equal to half integers, mu is equal to fractional powers, and you can look at it, and in this is discussed in this particular paper of 2012 with Professor Berry. Okay, so the details can be found, and I encourage you, the students, you can also take further, you can also consider further solutions. Also, please note, we are considering a very special case, the power law only, that a force is power law, but actually you can come up with much more difficult combinations or magnitudes of the curl forces, and then study the dynamics, like what new kind of intricacies, what new kind of dynamics it can lead to. Okay, but let me just, because there are so many interesting features, let me keep moving very rapidly, because I want to, the main idea of my talk here is just to give you a flavor of everything what we have thought about in last few years, and then, I mean, leave your fertile brains to come up with much more interesting possibilities and all that. So without getting into much depth of each idea, because there are so many ideas, I will just give you a flavor. So then comes the question, so far we have only discussed the mathematics. Question is, why should physicists bother about these forces? What is physical about these forces? One thing I should say at the very outset, that these forces are not the fundamental forces, but we already know that there are only 4 fundamental forces, or so far we know. Okay, so but then frictional forces is also not fundamental forces, but still we talk about those forces, right? So it's similarly like frictional forces, which actually can be written as electromagnetic attractions or gravitational attractions and all kind of attractions, attractive forces. Similarly, these forces are also effective forces, but they have. So now I'm going to describe a particular very important area where these forces appear in a very prominent form. Okay, so here comes the, consider the a particle, an atom kept in a electric field. Now, if it was a static electric field, what it will do? The positive charges will go in one direction, negative charges will go in the other direction. So the atom will become a dipole. But now consider an electric field. Instead of the static electric field or static electric field, think about the atom kept in the path of a light ray. So what is a light ray? An electromagnetic wave, and it consists of electric field and magnetic field which are oscillating. Even if the simplest one is having a, let's consider simplest one, you can consider a sinusoidal dependence. E is equal to E0 sine omega t or E0 cos omega t, fluctuating with the frequency omega, oscillating with the frequency omega. So a dipole now does not know what to do, because the moment it arranges, the atom itself arranges its charges, immediately after that the field changes. So the atom again has to rearrange itself, the dipole has to, so dipole starts fluctuating. But to fluctuate, it also starts radiating, because you know a fluctuating dipole, an oscillating dipole radiates, okay? But when it is not only that, the electric field is, if not only changing in time, if it is also changing in space, then what happens? Then the particle which is moving, the dipole which is oscillating, also feels the change of the electric field every time it oscillates, and it therefore there are other kind of dynamics, other kind of complexities appear in the problem, and it no longer remains a simple course or simple dynamics. Okay, so basically we are now going to consider the just the simplest approximation of a dipole oscillating in a electromagnetic field. Okay, so what are the degrees of freedom? Degrees of freedom is velocity. Velocity of what? Velocity of the atom, which has now become a dipole, and position r, and dipole moment p. So velocity in position r, because dipole has two particles, so basically we are going to talk about the center of mass motion. So velocity and position of the center of mass and dipole moment of the whole atom. Okay, or rather the dipole, I should say. So because we are talking about the center of mass of this dipole, so the center of mass motion is controlled by external electric field. Okay, and because these are Hamiltonian conservative forces, non-dissipative forces, and therefore volume is preserved in state space, work done is also around a cycle is zero. However, the third degree of freedom, that is the dipole moment P, is governed not only by the external fields, but by the net field. Net field which is constantly changing, and not only changing, or rather changing, because of a very important reason, that is because dipole is radiating. And dipole is radiating means dipole is somehow, there is a loss of energy. There is a change in energy, even if I don't want to use word loss. So there is a dissipation. So because dynamics is non-conservative due to radiation. Okay, however, in the state space, because the energy lost because of the internal dynamics, which is the dipole oscillation, internal dynamics here is referred as the dipole oscillation. Dipole oscillation, there is a loss of energy due to radiation. However, if you allow sufficient time to the dipole, that means if the dipole is moving very slowly or losing its energy very slowly, so it will immediately compensate its energy by absorbing the energy by the external electromagnetic field. Okay, so this is, so that means we are going to assume that the dipole is moving very slowly in this electromagnetic field. Adiabatic approximation, that's what I'll be talking about. Of course, I don't have to talk about this, but to build up, to see through, to build insight in any new physics, we have to start with a very simple model, and that's why we are doing it. Okay. So now comes the question. Actually, I always have two types of slides. One is where I summarize, other where I give mathematical details. So first, let me summarize what I'm going to do, and because I'm never sure how much time I'm going to have. So therefore, first I'm going to summarize. So basically, I'm going to talk about optical forces on small polarizable particles using the dipole model, because polarizable particle need not always be dipole. They can be higher order multipoles also. So this work is, first let me just say that this work is published in 2012 in Journal of Physics 8. Okay, so here is the dipole model, that you had an atom, it got separated, charge Q minus Q, charge plus Q, mass M, half M, mass, if atom is of mass M, so half M minus half M. I'm very sorry. Okay, half M, and the distance between is D. That means the dipole distance is D, and the position of these two charges is R1 and R2. Now, because dipole is, you can assume these charges connected by a spring with frequency, and this spring is oscillating. So that means I am using the simple harmonic motion of the dipole with frequency omega 0, which is a static frequency. But now, because the dipole is radiating, so you also have to consider with the damping omega 0. Okay, because it is, now the third thing is, because it is moving in a force field, electromagnetic force field, so it is, of course, it's a forced harmonic oscillator. Okay, even if you want to consider the first order approximation, so it is because if in the static field, if it was oscillating with frequency omega 0, so in the electromagnetic field, which is itself oscillating with frequency omega, it will have it will be subjected to a forced frequency, and of course, because of radiation, there will be a damping. So now what happens? How do I study? So basically the idea is to calculate the optical force acting on small polarizable particle. So let me again state what I'm trying to do. My basic idea is to show you that the curl forces, that means the forces whose gradient, whose curl is not zero, unlike the forces which you have studied so far in your physics education, very clearly appear when you put a small atom or when you put an atom in an electromagnetic field. Even in the simplest approximation, simplest model, curl forces appear very clearly. Okay, so this is my idea to talk about. Okay, so basically to show that, I have to calculate the force on the force on an atom which is kept in an electromagnetic field, and that's what I'm trying to do. My atom now has become a dipole, it is radiating, so therefore it is subject to, and if I want to model it by this dipole, because it is oscillating, so I try to model it by a spring. A spring is connected to two masses, and this spring is subjected to damping. Okay, so now I want to consider the forces acting on the spring, or rather center of mass spring, and how this spring is moving in the electromagnetic field. And then my basic idea is to show that the force, effective force, will turn out to be a curl force. That's the main idea of this whole discussion. And let me just summarize first, and then I'll give you more details as per the time. So basically what we are going to do, this whole setup is kept in an electromagnetic field. Electric field, magnetic field. These are charges plus Q and minus Q, mass half M, equal masses, and therefore I work out the electric field and magnetic field acting on this charge and on this charge. But they are also subjected to damping forces. They are also subjected to attractive forces. Okay. So act forces on the two charges to get force on the center of mass. Okay, that's how you get. So if you have a system, you want to consider how the center of mass moves, you consider the force acting on all parts and calculate the average force acting on the net force acting on the center of mass. Now what happens? This will tell you how the whole dipole is moving in the electromagnetic field. That is center of mass dynamics. And after that, you use that the center of mass is moving very slowly, that under adiabatic approximation, non-relativistic approximation, that will give you center of mass dynamics of dipole in an electromagnetic field. Okay. Now, the question is, this whole thing when you will study, because it will depend on the distance d, I'll show you, it will depend on the distance d. So, and you know that the dipole moment is given as P is equal to QD. Now, P is not the momentum, usual momentum. P is the dipole moment. So, P is the charge times the distance between two charges. So P is Q times D, where D is the distance between two charges. So, but if this is moving and this is oscillating, so P is also changing. Dipole moment is also changing. The question is, what is the equation dipole moment satisfies? Because that will also enter into your dynamics. And you need to know how dipole moment is changing. So therefore, you have to consider that equation also. You have to figure out how to consider that equation. Let me, and I think there is something more. Okay. And you will find when you work this out, whole things, a net force will turn out to be a force which will depend on the complex, which will lead to a complex polarizability of the particle. Okay. Let me not talk in riddles and give you more details. But I will go very quickly because I have to tell you a lot more. Okay. But all these equations you are familiar. So opposite charges, plus minus q, mass m, connected by a spring with frequency omega 0 and damping omega due to radiation. Total electric field acting on these two charges is of this form: ER cos omega t, BR cos omega t. Forces on particle exact. M is the mass, R1 dot is the position, R1 is the position, R1 double dot is the acceleration of that. So F1 is in the Newtonian physics is given like this. The Lorentz force, this is the first part is the Lorentz force at the position R1. And then this comes, this is your that simple harmonic, the Hooke's force, because a spring force, what you call a spring, spring force, that's what you call. And this is because that spring, this is the actually radiation force, D dot. D dot is the velocity of that spring. Okay. So velocity of the spring, I mean to say how the distance between the two charges is changing. So this also acts a role. This is kind of damping origin. This is the damping origin. Similarly, you can work out. How do you calculate the force on center of mass? You just sum these two, F1 plus F2, and you calculate. So the R, if R is the position of the center of mass, R1 plus R1 double dot plus R2 double dot divided by 2 multiplied with M will give you the force on the center of mass. You can write it like this. Now you simplify this equation. You dipole moment P is QD. In D goes to zero limit, you can show that the force on the center of mass of dipole, which I give a name FD, can be written in this complicated form. Of course, this from here to here, how do we go, is given in the appendix of this paper. If you are interested, you can go and check it. We don't have so much time. Actually, it is easy to see, and you can work it out yourself. Okay, so this is where what is E total? E total is given here, and V total is given here. Okay. But now, as I said, now this total force acting on the center of mass, because the whole idea was what is the force acting if you put a little atom in an electromagnetic field, you find the force acting is, actual force acting is F of D. Okay, so still, where is the curl force appearing here? That is what we want to know. But actually, it is still not in. It is still not in complete basic variable form, because you have a variable P here, and P itself depends on E. Okay, so you have to write everything in form of E and B. So let me first write down, because dipole itself is changing, dipole moment is changing, and therefore you work out that equation also. So dipole dynamics is P is equal to QD. Q, what is D? D is the distance, R2 minus R1, where R2, R1 are the positions of two charges. So center of mass dynamics of dipole. How do you work it out? You, as I said, you consider that spring model for the dipole, that oscillating dipole. Dipole is oscillating like an ideal spring, subjected to friction, as well as forced oscillations, or rather, to simply say, actually forced oscillation kind of forced oscillation picture. You must have seen this equation many times, where this side is given like some kind of general forced force, okay, external force. So P double dot omega is the damping, Omega 0 is a natural frequency, and you have to really solve this equation to work out P, and then substitute in what equation I showed here, f of d, and then you get your f of d. Okay. It so happens that you can simplify it this because these terms, many of these terms actually drop out in or rather this whole thing, these terms can be rewritten in this equation form under non-relativistic limit, and then it turns out when you substitute it here, I'm sorry. Okay, so I have to repeat myself because I have jumped a little bit. So I showed you that the force on the center of mass can be written in this form, and within the spring, forced spring model, you can write the equation of motion for the dipole moment in this form. However, in non-relativistic limit, these two equations, this equation for the center of mass force acting on the center of mass, and the dipole moment equation can further be simplified in by these two blue equations. So finally, this is the approximate equation in this form for the dipole, center of mass motion, and this is the equation for the dipole moment. But now you know, all of you know, that the solution of this equation is you can easily find if you are using the adiabatic approximation. Adiabatic approximation here corresponds to that the dipole moment is oscillating with the frequency of the applied field. That means if the electric field is moving in the frequency omega, then dipole moment is also oscillating with the frequency omega. You know, this is a forced oscillation, one of the solutions of the forced oscillation. So when you use this, then you can work out your alpha by substituting it here, where alpha is just the coefficient which appears in the solution. So basically, you are now considering this solution. You are assuming that if the electric field, which let me just show you, flash you again, this was our total electric field, and you are saying that the dipole moment is actually just proportional to this totally. Okay, and if you allow that, then you can write P as alpha times ER. So all that you need to calculate is alpha. And when you substitute this solution, you get alpha. However, now you see alpha, with this solution, alpha turns out to be complex number. Okay. So this is ultimately, you have worked out your P, because what is P? You have worked out alpha. So you substitute alpha here. You now know your P. So you can substitute P here. Okay. But P you have worked out as the time oscillatory. Okay. So f of d you get as not only position dependent or the position of the center of mass, but also time dependent. Okay. So of course P you substitute. So f of d, finally when you substitute P will turn out f of d will turn out to be of the form of position as well as time. Okay, so you can now consider an average force, and averaging is over one time period of the electric field. So when you calculate that then you will find out, because there is you actually want to calculate, it makes sense that how over one oscillation of the electric field, what is the force acting on the center of mass of the atom. So if you want to ask that question and you work that out, then it comes out to be in this nice form where alpha star appears, which is a complex conjugate of alpha. Alpha was a complex number, and you find that del cross F is you now calculate del cross F, and you will find del cross F is not zero only if alpha is a complex number. Okay, so basically what I'm trying to say is, let me again show you. If the small particle, the atom which I said initially, has a complex polarizability, alpha is alpha 1 plus I alpha 2, kept in a monochromatic electric field, then it is acted by a force, an average force, which can be written in this form, which I showed you in the previous slide. And then you can separate this force, you alpha star. So if you write the real part as alpha 1 and imaginary part as alpha 2, you can separate it in two parts. It turns out to be of this form. Now you take the curl of this. It is easy to take the curl of this, okay? And this turns out to be this form. You see curl is not 0 only if this term alpha 2. What was alpha 2? Alpha 2 was the imaginary part of the polarizability. So if alpha 2 is not 0, curl is not 0. So basically what I am trying to say, when you put a small particle in a monochromatic electric field, if it has complex polarizability, its curl will be not 0. Okay, so this is a very clear, because I have not done anything. We have done the standard physics so far. I have put a particle in a electromagnetic field, and this particle is allowed to radiate. Allowed, of course, not allowed to radiate, it will radiate. That's what physics tells us. And this is even under the simplest adiabatic approximation and non-relativistic approximation, you can show there is a mysterious force acting, which is not falling in the category of Hamiltonian formulation or the Lagrangian formulation, or which is violating the Noether's theorem. Okay, so this is the, I'll not, okay, there are a lot more details, but I'll not go. So what I have told you so far is that in optical cases, curl forces require particles with internal structure. Internal structure means that there is a internal structure means there will be a non-zero part of the polarizability. Okay. The external force on separate charges are in the dipole are Hamiltonian, Coulomb and Lorentz. The curl force therefore reflects the influence of internal dynamics on center of mass dynamics of the dipole. To maintain the dipole oscillations, the energy must be supplied by electromagnetic fields. Okay. Otherwise, after some time, the dipole oscillations will stop. So in that sense, electromagnetic fields are preserving the volume, are satisfying the Liouville equation. However, the internal variable, that means P, while the center of mass, because of the other variable P, the center of mass is subjected to a curl force. Okay, because of the dynamics of the dipole moment, P, the center of mass variable, whose R, center of mass variable R, is subjected to a curl force. Okay. So, okay. So, all the internal structure must be dissipative. That means dipole radiation from the particle. The motion that curl force generates is not dissipative. That I have already said, because every time the electromagnetic field replenishes the lost energy. Okay, so that's how it maintains the volume preservation. This particular thing, now I won't have much time because there are so many still things I need to say. So, but let me just flash to you if you already know this. This is in contrast with familiar irreversibility in Brownian motion. In Brownian motion, if you know that a big particle is moving in the field of small particles, and these small particles are applying frictional forces here. So there is a macroscopic friction, and because of macroscopic friction, there is a macroscopic irreversibility. Although there is a microscopic, at a very small level, the dynamics is reversible, but at macroscopic level, the dynamics is irreversible. Okay. However, here is something just opposite. Here, the irreversibility is coming at the microscopic level because of the internal dynamics. At the electromagnetic field level, there is no irreversibility because they are all Hamiltonian forces. But at the loss of energy is occurring at the internal degree of freedom, and therefore there is a microscopic reversibility. And this question is important because if let us not forget that the macroscopic irreversibility consideration in Brownian dynamics are also connected to very important ideas of increase of entropy and arrow of time and those kind of questions. So I am now telling you another fundamental aspect of these curl forces, especially in context of optical cases, that is an internal dynamics which corresponds to microscopic irreversibility is needed for curl forces, effective forces to appear as curl forces. And the one another one I've already told you is Noether's theorem. Curl forces do not satisfy Noether's theorem. Okay. So here I'm posing a question. Can the dynamics of an object with internal dynamics be determined by a curl forces if the internal dynamics is not lossy? Okay. So this is what I'm leaving you to munch on. Okay. So now, so far what I have said. No, let me just, okay. See, unfortunately, my slides are written for Blackboard, projector presentation. That's why you see every time, there is pauses and all that. So that's why I have to move every time I go through the talk. It is supposed to come one line after another. Okay. So now let us move to classical dynamics, because I think many of you probably will be interested in knowing about that. How does curling as a force influence the dynamics in state space? Okay. No Hamiltonian in general, no energy surface in phase space. Is the motion ever confined? No dissipation in volume. No dissipation, that is volume preserved in state space. Same for conservative forces in phase space. What does it mean? How does it affect the dynamics? Is there chaotic dynamics in state space? Is chaotic dynamics defined in same way? Lyapunov exponent, symplectic structure, Poincare recurrence, the usual thing we know about the phase space picture, Hamiltonian formulation. Okay, all that. What is the meaning of all those things in this context? Is the periodic orbit structure same? So basically, I'm just asking. Okay, fine, curl forces, the best way to describe curl forces is in the state space. Okay, what features of the phase space formulation of the conservative forces you can directly bring to state space in context of curl forces? Okay, that's the basic question. Okay, so whether CAM surfaces exist or not. So let me now move to the curly chaos, the chaos due to curl forces, and that I will, because as I said that curl forces appear in a very realistic way in optical cases, and therefore I'm now going to use a optical system, and let me give you an introduction because students may not be familiar if you are in MSc, but you are familiar with all these equations. I'm just connecting it to you, connecting you to these equations. So this is your usual electromagnetic wave equation, del square, 1 by c square del t square. U is the intensity. It can be E or B. Now you write it in the E form. You find the time independent form, like Schrodinger equation you do. It's a Helmholtz equation. You can write it in this form. What is K? K is related to the frequency of the light wave, and C is the electromagnetic wave, and C is the speed, and you can get in this form. Now you try to solve this equation in a simplest one approximation, which is called the paraxial approximation, which is a very standard approximation used in almost many areas of optics, that the electric field varies very slowly in one particular direction along its axis, along the axis of its propagation. Okay, so if Z is the axis of its propagation, you assume the electric field is varying very slowly. So basically, you are assuming this is the approximation you are making, where K is a wave vector. So this is a mathematical form. Physical statement is that the electric field is varying very slowly, and all the variation of the electric field is occurring in the perpendicular direction of the direction of. Okay. So if you do that, then you end up with this equation. Okay. And this equation has you can see that the solution of this equation, now you can separate this because this part depends on x and y only, this part depends on z, you can separate this. So the solution of this equation is eikz, solution of this part is psi xy you have to determine. Okay, and EP comes because of the polarization, and we assume that it is a uniform polarization. Okay. So this form, actually Peroxial approximation is quite often used for Gaussian beams, and it is approximately valid for Gaussian beams, and most laser emit beams that approximately take the form of the Gaussian beams. Okay. For example, here, now I consider this is a picture of the beam, if you don't know what a beam is, because I found while discussing with some of my students, beam of rays, okay, many rays. Okay, and all these rays are traveling, so you assume that all these rays are traveling in the same form. Now you are talking about the electric field of all these, net electric field of all these beam of rays. Okay, and you say that you can, let us say that the electric field is given in this form. Question is, if there is a particle, let us put a particle red shown by red here in this field of, in this beam of rays. What force the particle will feel in the region where psi xy is 0? Because look, electric field is still propagating, but it now depends on psi xy. Now consider a situation where psi xy goes to 0. Okay. Question is, what force the particle feels in that region? And this region has now become very important. Okay. This region, I see some question.
Yes.
Okay, you work it out yourself. Okay, so basically the Peroxial approximation is given. I have taken it from the papers, so that should be. So basically, okay, if you think that there is this Peroxial approximation should be different, so this is the electric field I am focusing on. Okay, let me go back. One of the questions is that oh, I should go to that. Yeah, one of the questions is that the Peroxial approximation should be slightly different. Okay, so I will rather say that, okay, so let's not spend time on discussion of what is the Peroxial approximation, the exact form. I'm using this. I'm interested in this form of the electric field. Okay, where the intensity depends only on psi, on x and y coordinates. Okay, and there is a uniform polarization, and this is the direction. The z dependence only enters in this form. This is what we have. I'm thinking about. Okay, and now if you consider the beam of rays and kept a particle, the question is what happens in the region where psi xy goes to 0. So this is what. And I'm now going to claim this is very important region. This region has now become very important and this is a region where curl force appears in the most dominant way. Yeah. Okay. So, okay. So now this connects you to a very important area of physics, which is now being studied with great interest. That is singular optics, or OAM, or optical vortices and all that. And so, what is an optical vortex? Optical vortex is an electric field. Okay, optical vortex actually appears in a beam of electromagnetic rays where electric field is given in this form. Okay, and psi xy can be described by this form, and this is basically referred as the optical vortex. And if M appears here, so this optical vortex is called optical vortex of order M, and if B is 1, then it is called isotropic optical vortex. If B is not 1, then it is called anisotropic optical vortex. So basically, optical vortex is basically, so far, it is basically giving you the intensity of this electromagnetic field, or rather electric field. And why it is called vortex will be clear to you, or rather it is clear right here, because if x and y, x is equal to 0 and y is equal to 0, then this intensity, this amplitude goes to 0. Okay. So their electric field goes to 0 at that point. Okay. And why it should be interested? Because now you look, if you have this kind of electric field, now you substitute in the curl force equation, which I have flashed you, which I showed to you. Let me go, just remind you again, what was the curl force equation? Curl force equation was somewhere here. Oh, hold on. Yeah, here. This was the curl force equation, and it was just obtained by working out the center of force acting on the center of mass of the dipole, and then substituting the dipole degree, the dipole moment, how dipole moment varies, using the simple harmonics forced oscillation approximation and non-relativistic approximation. So this was a force. Now you substitute electric field E here, and then it turns out to be of the form you substitute this electric field with this psi, and you get the result in this form. You can work out curliness turns out to be of this form. Now you see, the interesting thing is, which might your differential equation inclination people might be interested. For B is equal to 1, it turns out to be again a Hamilton-Fowler equation. Okay. Or rather, an equation of this form. Very simple case of Hamilton-Fowler equation. Okay. So okay. Now, another thing before I move forward, let me, because now the question is, okay, what I'm going to do, I'm going to study the dynamics of these equations. Because I'm interested what kind of dynamics these equations have, because these equations are directly related. What is R? Let me remind you. R was the center of mass motion. So this equation is now describing how the center of mass of an atom, which has polarized, moves in an electromagnetic field with the Peroxial Approximation and near an optical vortex. Okay, so this equation is describing the dynamics of a small polarizable particle near an optical vortex. Okay, so we know, and this is for B is equal to 1. For B not equal to 1, it can be more complicated. So question is, can this equation, this is a differential equation, and can this equation lead to chaos? That's the question. Or more complicated cases when B is not equal to 1. Or this is the result for a single vortex. Suppose if we have a family of vortex, can it lead to chaos? That is the question. So we need to now study this equation numerically. So first of all, we have to study create an optical vortex numerically. And this is done, of course, by Professor Sir Michael Berry. And okay, if you want more detail how he has obtained this equation, you have to ask him. But basically, it is just the monochromatic superposition psi or of 10 plane waves. 10 plane waves of this type, which I showed you. Okay. These are, okay. And then all with the same wave number. And this is a phase space plot. Not phase space, sorry, phase plot of the local wave vector. How you define the local wave vector? Local wave vector is defined by taking the gradient of the argument of the wave psi r, and then you plot this, and the color coding is such that it is describing the phase. So you see the point where the phase is, so if at a point phase is taking different, if you see many colors, many different colors, so that means near that point phase is changing very rapidly. Okay, so phase is changing very rapidly. What are these points? Because these are the points, see, phase is given here by kr. This is the local wave vector. This gives you the local phase. And local phase, as I said, this is the definition of the local phase. The gradient of the argument of psi r. Naturally, if psi r is 0, k of r is 0 in that point. However, slightly away, you see, yes, there are points where it is 0, but just slightly move away. There are a lot of colors, and color coding is such that change of color indicates that phase is changing very rapidly. Where is psi r is equal to 0? As I said, psi r is equal to 0 corresponds to the origin of the optical vortex. X is equal to 0, y is equal to 0. So these are the origins of the optical vortex. And as you see, near the origin of the optical vortices, the phase is changing very rapidly because all kind of colors are mixing near. And the question is, now if a particle is left in the region nearby, what kind of dynamics it is subjected to? As I already showed you in the previous slide, the dynamics you can work out turns out to be the force acting on the particle near an optical vortex turns out to be a curl force. An equation, the center of mass of the particle describes this equation if the optical vortex is isotropic. Okay. So now comes the question. So let us now study the dynamics as in the state space, like we do in the phase space in the ordinary cases, which you are so familiar. However, in this case, as there is no Hamiltonian and there is no Lagrangian, so there is no energy surface. So therefore, to study, even if you have, let's say, consider just 4 variables, that the center of mass has x and y, position x and position y, and velocity vx and vy. So still it's a 4-dimensional space. And in this 4-dimensional space, you cannot consider the energy surface because there is no energy surface. So you cannot consider Poincare surface of section because Poincare recurrence is not applicable here. Because, okay, so question is, how do you simplify this? Like in the case of phase space, we use the surface of section plots. What do you do here? So Professor Berry came up with the idea that let us consider volume of section. And how do we consider the volume of section? Like similar to the Poincare surface of section, we fix one coordinate and consider the 3-dimensional plot, and that's why it is volume. Okay, so if we fix, for example, x is equal to 0 and choose time, every time x is equal to 0, we look at the other coordinates at that time and just keep track of those variables. So we choose every time x is equal to 0 and plot the corresponding variables y, vx, vy, and okay. So then it turns out to be a 3-dimensional space, and we call it volume of section. And because you could have chosen, instead of x is equal to 0, you could have chosen y is equal to 0, or vx is equal to 0, or vy is equal to 0. So this way you get 4 volume of sections, this, and this. So you see, all these points are lying on some kind of surface. Okay. What does this mean? So although I said, in principle, there is no Hamiltonian, there is no energy surface. But when you plot these points, and these points are for the equation I showed you for a single vortex case, this equation which I showed you, this equation, I'm plotting now this equation in the state space. Okay, so So you see, still they seem to lie on a surface. You go to the another volume of section, still they are lying on a surface. Although there are, look at these points where there is no point is entering, although you keep going on, keep going to higher and higher times, still these regions remain unfilled. Okay, so now you consider, let us consider 4 optical vortices. So that means not only one optical vortex. So now you are considering a particle. Let me remind you. Initially, it was only one optical vortex. That means you had kept a particle in this electric field. Now you are considering an electric field which is a combination of 4 electric fields. Each electric field contains an optical vortex. Okay. So what happens in that? Because now you want to see, because you saw in one optical vortex case, you are seeing a surface of some kind of hidden constant of motion. Some kind of surface is still appearing. It is not. So question is, what happens if we further make it? So again, you do the volume of section plots, and now you see, although still there is some kind of surface appearing, but on that surface, they are still filling the entire thing. Okay. So we refer it as the question is, okay, is it a real surface? Suppose if I leave it for a long time, will this surface remain? Because within the computer, limitations we have done. And by the way, all these numerical plots which you are seeing is done by Professor Berry on Mathematica. So, so you see, although here there is no conserved quantity, no dissipation, but if you just look at these plots, they seem to suggest there may be some hidden conserved quantity in state space. Okay. Then this is another thing. Actually, this is a 3-dimensional picture which I could have rotated, and you will see it will always remain like this. And I showed it just to attract your attention, although I should have rotated it 360 degree. But let me now leave it to you. Okay. Now the question is, am I just talking idealistically or mathematically? I have showed you that this appears. No, actually this is the concept of optical trap, and this has already this has already been given a Nobel Prize. And of course, when Ashkin introduced this idea of the optical trap, he did not know that he was talking about the forces, curl forces. He did not know that these forces are very different from the usual forces. So let me go to the complete slide. Yeah. So uniform polarized if you consider an optical trap, this is the electric field which is applied, the force acting on the trapping of a particle inside an optical trap contains of 2 components. One is a trapping force, the other is curl forces. F trap is given of this form, and which is called also known as optical tweezer, and F curl is of this form, which is actually the same as the scattering force of the Ashkin, who got Nobel Prize in 2018, I think. So, okay. Okay. So comes the last question, because I see I'm running out of my time, and therefore let me just quickly tell you, the question is whether Hamiltonian curl is possible. The Hamiltonian curl is possible because, the question is like this: what do you want to know? Whether these conditions, that del cross F is not 0, and the Hamiltonian condition that R dot is del H by del P and P dot is minus del H by del R can simultaneously be satisfied. Okay. Basically, if you take, so it turns out to be, if you combine these 2 conditions, you basically want to find out whether this thing, what comes out is non-zero. Okay. It so turns out that at least we can find out one case where it is possible, Hamiltonian with anisotropic kinetic energy, of this form. Not the standard ones. You see, you don't come across. But then let me, now I'll go very quickly because I see I'm running out of time. You can do the same Hamiltonian equation business and see, if you write down the Hamilton's equation in this case, you will find x dot, y dot, because this is the equation. You can write down from h, you can write down x dot, you can write down y dot, from there x double dot, y double dot, and then x double dot gives you fx, fy, x component of force and y component of force. It turns out to be of this form. It's just because of this coefficient matrix M in the beginning that if you now calculate del cross F, that is not zero, although it is still scalar potential. But because of presence of this matrix M in the start, del cross F is not zero. So Hamiltonian you can define, but del cross F is still not zero. You can go, I mean, like this case we have discussed in this paper in great detail. You can look at it. There are some cases we have discussed. The special case of these Hamiltonian curl forces is that the periodic orbits you can study, but they have spatial nature. They should be self-retracing and self-crossing. And there are other special features of these periodic orbits. These are not the periodic orbits of the standard Hamiltonian type. And now you know this kind of, but there is a very standard thing we have already looked at, anisotropic Kepler Hamiltonian, which is of course of this form. Okay, so basically the curl Hamiltonian is anisotropic Kepler Hamiltonian is that example. Okay, so I had other things to say, but I'm not going to now. Will be able to say you can calculate the spectral statistics of. Okay, the question you would like to ask at this stage is how curl force manifests in quantum dynamics. So, but this question, without knowing that they were talking about curl forces, has been addressed in context of Kepler Hamiltonian. People have an isotropic Kepler Hamiltonian. People had studied the spectral statistics of an isotropic Kepler Hamiltonian and found that they are not really at the time when everybody was seeing a GOE or GUE in chaotic systems. The Kepler Hamiltonian statistics turned out to be not GOE, GUE, but rather between Poisson and GOE. So actually, in spectral statistics, people had already seen difference from the standard chaotic systems, quantum chaotic systems, without knowing that Kepler Hamiltonian falls into the classes of Hamiltonian curl forces. There are other quantum features discussed by Professor Berry in some separate papers with other people, and I don't have time because I'm running out of time. Okay, so do I have time to summarize now?
Yes, madam, you have time.
Okay. Okay, so let me now give you some kind of like, I like this because when I was doing my high school, I was asked to make these kind of tables. So I like these tables. They are very clear to me. So curl forces non-Hamiltonian. Curl forces Hamiltonian. On red, curl forces only state space formulation, only phase space formulation. Motion, curl forces non-Hamiltonian, not confined. Motion confined to energy surface because of Hamiltonian. Noether's theorem irrelevant. Noether's theorem not applicable. Curl force Hamiltonian. Mind you, I'm not talking about standard Hamiltonian, curl force Hamiltonian, like anisotropic Kepler Hamiltonian. Least action principle not applicable. Curl force Hamiltonian least action principle applicable. No symplectic dynamics. Symplectic structure of dynamics exists in this case. Poincare recurrence theorem not applicable in curl force non-Hamiltonian. Poincare recurrence theorem applicable. No dissipation, volume preserved in state space in curl force non-Hamiltonian, same here. Say periodic orbits are of the same type for both the cases. Okay. Yeah. Actually, we have not studied this, so I don't know why did I write this. We have not studied the curl forces, periodic orbits for the curl force non-Hamiltonian, so I should remove this. Last one is wrong, but this side it is correct. Okay. So we have not studied. Okay, so let me put a question here. The curl periodic orbits in the state space will be self-retracing, self-crossing. The question is that we have not studied, but it seems it will be so. Okay, so this was the curl force non-Hamiltonian when you don't have a Hamiltonian formulation, and curl force when you have a Hamiltonian formulation. Next is Hamiltonian curl, and when you don't have when you have non-zero curl forces, when you have zero curl forces. So Hamiltonian in both the cases, but the curl of the force is not zero, and here curl of the force is not zero. Comparison. Both the cases phase space formulation is possible. In both the cases energy surface is possible because of the Hamiltonian, of course. Notice this is also same. However, this thing is now takes a different aspect. Periodic orbit need not be self-retracing, self-crossing in this case, as you already know all this. But in this case, periodic orbits have to be self-retracing, self-crossing, because along a closed circuit, closed orbit, closed periodic orbit, velocity in state space is conserved. Okay. No cam surface in an anisotropic Kepler problem. People have already seen breaking of Cantori lead to transition from integrable to chaotic dynamics. In this case, cam surface exists. Okay. Then the last one, I think, can curl force appear alone? Because now some of you may, this is the last slide, I suppose. No, this is not, but I think I will stop. Okay. So betatron is very well known instrument. So basically, in a betatron, you have a vector potential particle moving in a vector potential of this form. T, Fr is an arbitrary force. So naturally, if the vector potential is there, you can have a Hamiltonian formulation of this form, standard formulation. Now you calculate the total force from here. Total force turns out to be of this form. Of course, if you calculate the, if for us, depending on the nature of the force, this delta cross F can have a delta cross F need not be zero, because del cross F, if del cross F is zero, then only F total will be zero. But then in this case, F total not only contains this part, but it also contains this part. So although you have in the betatron, depending on the choice of the force, you may have curl forces also. However, they always appear with a velocity dependent force. And as I had already said in the beginning, we are more interested not in forces. We are interested in forces whose curl is not zero, but they are only position dependent, not velocity dependent. Because forces whose curl is not zero and who are velocity dependent, such forces have already been known. For example, magnetic field is one such, magnetic force is one such force. Okay. There is a lot of discussion about curl forces in engineering physics, whirling shaft, pendulum with rotational dissipation, thrust from rockets, water hoses. These are also known as follower forces, circulatory forces, pseudo-gyroscopic forces, and okay. By the way, for students, a follower force follows the transformation of the body in a way such that the work done by the force is path dependent. Follower forces are very well known forces in engineering physics. There is some controversy in engineering mechanics. I have written a very nice article by Isaac Elishakov, and I will encourage you to look at it because it's a very beautiful article and he discusses pros and cons. So let me now summarize. And I'll go to the last one, yeah, because I don't have time. Yeah, okay. So curl forces, Newtonian forces only position dependent, non-conservative with non-zero curl but non-dissipative. Hamiltonian curl forces generated from Hamiltonian of special type in which kinetic energy is an anisotropic quadratic function of momentum. Non-zero curl condition imposes restriction on type of periodic orbits in phase space. Spectral statistics transits between Poisson and GOE with anisotropic parameter, but this has been studied only in context of anisotropic Kepler Hamiltonian. Unambiguously present as optical forces on small polarizable particles in electromagnetic fields. Govern electron dynamics near a screened impurity in a semiconductor, like we know anisotropic Kepler Hamiltonian takes appearance there. reveals non-applicability in irrelevance of Noether's theorem. Open questions. Many open questions. I have just written some which appeared to my head. Let me just go to the last one. Can more general curl forces be generated by Hamiltonian? No symplectic structure. A lot of work to be done in symplectic. How does the quantum mechanics of Hamiltonian systems with curl forces differ from those without curl? In general, curl forces dynamics need not be generated by Hamiltonian. How to quantize? Can other types of vortex field, classical fluids, superconductors, and superfluids can generate forces of curl type? And so many more questions. Here are the references. Thank you very much for your kind attention. Hope I have been able to give you some flavor.
Yeah. Now, the session is open for questions. Discussion.
Thank you very much, Shukla, for a very nice, Pragya, for a very nice presentation of your work. Very enjoyable. I'm not really very familiar with curl forces, but I wonder whether these dynamical systems with curl forces can admit non-standard Hamiltonian, non-standard Lagrangian. And,
yeah, so
we are familiar with velocity-dependent force. For example, even a damped harmonic oscillator admits a Lagrangian and Hamiltonian formulation, but non-standard, quite complicated. But there are other systems like Leonard-type systems with position-dependent force, position-dependent velocity force. So they admit very complicated but interesting Hamiltonian, Lagrangian. They can be quantized and so on. So I wonder whether these curl force systems can admit such non-standard Hamiltonians.
see, if by non-standard Hamiltonian, you mean to say this where kinetic energy is some kind of yeah. So of course they will. I mean, there is this is an open question, and one has to. I think Guha has written many papers on it. But as Dr. Berry has always maintained that this actually already a lot of ideas are there. What is not known is the force is only position dependent, not the velocity. Okay, then what happens? The novelty about these kind of forces. If the force is both velocity as well as, is there any interesting dimension? Is there any it can lead to new kind of dynamics which is not already incorporated by Hamiltonian formulation? This is still an open question. And I think. I mean, Hamiltonian formulation, the kind of which I talked about, should be possible in some cases, but not for all the cases. I think Michael Berry is trying to say something. Yeah.
Yeah.
Yes, Michael. Do you want to answer it better?
Yes, I can say a little bit about this. Of course, we worried very much about this question that Professor Lashman is asking. Now, there are a number of different generalizations. One which we regard as empty, where any dynamics can be written as a Hamiltonian, is if you double the number of degrees of freedom. Now, that's a purely formal thing, and it doesn't really give any additional insight. So in order to understand whether there's some hidden Hamiltonian structure which we just weren't able to find, we did this numerics that Pragya has described a little. And we found that in the case she first showed, it's actually two vortices, not one, Pragya, that there was this hidden constant of motion. Because when we looked at this surface of volume of section, we saw there's a surface there. We don't know what that constant of motion is, but there is one. Now, that doesn't mean there's a hidden Hamiltonian, but it means there's some structure. However, once we had four vortices, and actually I think it would be the same for three, then it's very clear, and we ran the programs for a very long time and controlled the accuracy, that there is no surface in that space. So we have the unusual situation in chaos theory of some system that explores a four-dimensional state space or region of it, fully four-dimensional, no apparent conserved quantity at all, and yet is non-dissipative, so no strange attractors, nothing of that kind. So this led us to conclude that there really is no Hamiltonian structure of any consequence. There may be some formalization in which it might appear Hamiltonian, but not in a way that gives any insight, because there will be no conserved quantities. So that's why we think, in the absence of any contradiction, that's why we think that these curl forces really do represent an unusual kind of dynamics. And it's actually rather strange to us because, you know, almost the first thing you say in Newtonian mechanics is force depends on acceleration. And if you then don't say that the acceleration, that the force is gradient of a potential, if you don't say that, you immediately get this class of curl forces. But whenever we present dynamics, and for good fundamental reasons, we do immediately introduce a scalar potential. Now, just one more comment. As Pragya mentioned, there is this class of curl forces involving anisotropic in the momentum Hamiltonians, where which are Hamiltonian. But this is a very restricted class. So we argue in our paper, we can show that this does not apply to general curl forces. So although it's an interesting case, and we wrote a paper about it, it shouldn't distract from the argument that the curl forces in general really are not Hamiltonian. I think this needs further study. I mean, someone like yourself, who's more familiar with these non-standard Hamiltonians, maybe should have a serious look, just in case we've missed something.
Michael, I think that's what his, I think he was asking if you assume that the forces are also velocity dependent.
No, that's a different thing. That's a different.
No, the position as well as velocity dependent. So question was whether you can have some non-standard.
Yes, well, it depends what you mean by non. Of course, ordinary Lorentz forces, of course, velocity dependent, and then we then know that the curl of the acceleration is not zero, but that's a different situation from what we're discussing. We exclude that explicitly in our papers.
I think this is the questions you are asking, Professor Lakshman. It is still complete. It's a completely unexplored domain. A lot of new things are there, possibilities are there, and that's why actually I chose this topic. Because school is the school which can really bring the juices out of it.
Okay.
So,
yeah, I think there's
yes,
a lot of interesting things to do. Okay, sure.
Yeah, we just should mention one thing, that someone who has looked at curl forces, but in fact has slightly confused matters, although his papers are perfectly correct, by considering velocity-dependent cases, is Pythagoras. I mean, he's written a number of papers stimulated by ours, mainly the mathematical aspects, but it's just worth mentioning that he has taken up the idea, but not the aspects that we would like to have taken up.
Okay. Okay, thank you very much. Thank you.
Thank you.
So, any other questions? I think there is a question in the chat, madam. The last one.
yeah. Okay. Can we conclude that whatever symmetrical mode we see in multi-mode optical fiber correspond to some conserved quantity? Okay. Well, I mean, that's I'm not an expert on fiber optics, and therefore a correct person to answer this question will be a fiber optics person. However, what I can say is that I mean, whatever I have talked about so far is it is not. I will not so easily conclude about it. Okay, because optical fiber, as I said, there are effective forces appearing. and these effective forces are pure forces which don't have, need not, Noether symmetry is not really applicable, Noether theorem is not really applicable. So whether the conserved quantity has symmetrical counterpart or symmetry has the quantity counterpart, it's not so obvious. So it's not, one has to really explore it. Okay. Now, second question is, in practice, we don't have monochromatic EM wave. So may in experiment, do we have more complex chaotic dynamics in optical vortex? Of course, that's a very good question. And people have actually streamed optical vortices with noise. Although, because I'm not an experimentalist, and I do not know how difficult it is to really have a monochromatic EM wave, you see, having anything mono is in principle just against the nature. Okay. So basically, but when we say mono or one dimension or one single chromatic, basically is an approximation. So depending on what kind of, how good an approximation this is for your system, it can still be monochromatic and you don't have to worry about noise. However, in general, yes, there are people who have looked at optical vortices where with electromagnetic waves, I mean, the psi xy which I told you is not so well behaved. It's a kind of random function. And then what happens? Of course, it will lead to chaotic dynamics. Actually, it will lead to more chaotic dynamics. It will add up to chaos. Yeah. So, yeah.
May I say something?
Yeah,
well, actually, about both questions.
Yeah.
I mean, about the multimode fibers. I mean, inside fibers, if you have optical vortices, I mean, whether the waves are linear or non-linear, if you consider the motion of small particles in those fields as small absorbing particles, dipoles, then it's very likely that you will see the kind of chaos that we found with four vortices. I see no reason why it should be less complicated. But with respect to monochromatic, I mean, all models in physics are, of course, approximate. And whether you need to consider deviations from the approximation depends on what you want to study. Now, of course, lasers have their line width, so they're not precisely monochromatic. But it's such a good approximation that we felt that we first ought to understand the complexities that you can get with monochromatic waves, which already, as Pragya showed, are quite considerable, before we would consider the tiny effects of non-monochromaticity. And I'm sure it would give more complex dynamics, but I think first we should understand the monochromatic case. It's complicated enough. I mean, this is our attitude. I mean, if you have a motivation to study non-monochromaticity, then of course do it.
Yeah, actually, I'm holding a paper which discusses control of diffusion of nanoparticles in an optical vortex lattice. So actually, Prashant, there are people who are already looking at this because of the noise in the field, this diffusion of nanoparticles kept in that kind of electromagnetic field. So if you are interested, this is archive. I can type it later on. So yeah, so your questions are very valid.
Okay, ma'am.
So,
Ma'am, actually, ma'am, you considered the four optical vortex case there.
Yeah.
So was that like kind of bandwidth, the bandwidth of the electric field, or just any random electric field it can be taken for the four optical vortex?
No, I described to you that we had taken the way we had created the optical vortices. Actually, again, Michael Berry will be the best person to answer because he has created that. Michael, would you like to answer?
Oh, okay. If this was about the core of the optical, I mean, within classical electromagnetism, these cores are strictly zeros, right? They're zeros of the field. But as Mark Dennis and I showed, they're also windows down into quantum optics in the sense that they are they're kind of windows through which you can glimpse the chaotic seething of the quantum vacuum, in the sense that you can get transitions if you put a particle there, transitions to modes, vacuum modes, which are not the modes that you've excited. That's a small effect. I mean, we calculated what the width of the of this window is inside a vortex. It's much smaller than the wavelength, because it involves Planck's constant. It's quantum. So that's an interesting thing. And Pragya mentioned the paper with Stephen Barnett, which where we look at the way in which a different quantum effect, the way in which vortices can provide the momentum, the high momentum near a vortex, even though the intensity is very small, the momentum is very large, the phase gradient. That would kick that small particles placed there. As a different aspect. But with the cores, as I say, there are these windows into the quantum electrodynamics beneath. And we were a little bit disappointed that 16, 17 years, 18 years later, nobody has taken that up, because I think there's something for experimentalists there. There are effects to actually see the quantum cores.
Can I interrupt you, Michael? I think this question is how you have this 4 vortex picture. How have you created? That is my question to you.
How come? What was the second part?
4 vortices which were used in our this thing. How were they created? So waves.
I see. Yeah, that's very easy. I mean, you just create a scalar wave with 4 zeros. I mean, that's not, and you can easily create them with alternating signs, so that the total the total angular momentum, if you want, is 0, the total vortex strength, and this is what is responsible for the particles not being kicked out to infinity. So it's easy. You can create a function, a scalar function with 4 zeros, and optically, you do it by interference.
Yeah, Prashant, can I add? Actually, I have found a lot of literature on internet which tells you how to create optical vortices out of monochromatic waves. Okay, so yeah. So if you really want to create and study, I think the best way is just noising and all possibilities, using Gaussian beams, using Bessel beams, and all kind of possibilities. Which is discussed.
No, you use a spatial light modulator. This you can create anything, any phase distribution you like, and this is done in practice. So, for example, something much more elaborate than the simple vortices that we are describing in this work, Mark Dennis and I showed how you can create vortices in 3-dimensional space which are knotted or linked. And again, this involved imposing a predefined phase distribution on a propagating beam, and Miles Padgett and now others have actually implemented these vortex knots experimentally. So you can really, essentially nowadays, they can create anything you like. Spatial light modulation is one method, but it's very powerful.
Okay, sir. Okay, thank you so much, sir.
Prashant, do you have any other question?
Yes, sir, I could understand now, but just I had difference that in the experiment we'll be using a monochromatic, maybe a laser.
Yes.
So that particular laser will have a band of those wavelength.
It is very important to have a finite bandwidth for creating optical vortices, So.
Okay, ma'am. Okay.
Yeah.
Yeah, ma'am. Okay, ma'am. I need to think about it more.
If you take laser is the best one.
Yes,
so,
yes. I have to go through those things actually, ma'am. So thank you so much, ma'am. Thank you, sir.
Professor Ambia, do you have some questions? So any other questions?
Yeah. Very nice talk, Pragya. I was just wondering, when you talk about self-crossing trajectories, normally we say state space trajectories never cross, right?
Yeah.
So how do you interpret that? Because self-crossing means it is against determinism.
It's in configuration space.
This is in configuration.
Configuration space. Even in configuration space, can they cross?
No, yes.
Yes.
Of course, they do, but not in phase space or state space.
Okay.
No. Let's just go there and see. I mean, see what we say, and let me just. It's a very simple thing. Okay. Let's just look at that because I had to go very quickly. So it is here. Can you see this headline?
Yeah.
So let us question it, and maybe there is something very important here. So a periodic a closed curving position velocity space. Okay. The kinetic energy must be unchanged after each traversal, right? Because the kinetic energy is either you define kinetic energy in some very non-standard way, or if you define kinetic energy as half mv square, then if velocity comes back to itself, then kinetic energy comes back to itself. Kinetic energy must be unchanged after completing the periodic orbit, right?
Okay.
Now you consider the periodic orbit dl marked by the perimeter marked by dl and e by dl. So this thing should be 0, right? You can simplify this. V dot dv, open this because dl goes away. So V dot dv is equal to 0. So what does this require? You can rewrite this whole thing. V dot dv is equal to 0. dr dot r double dot. Exactly. Because V is dr by dt and dv, take dt here. So it becomes dr dot r double dot.
Okay.
So now what is r double dot? R double dot is the acceleration. Dr dot f of r. Okay. So now the closed circle on v dot dt is equal to 0 requires dr dot fr is equal to 0. Okay, it should be closed. Okay. So dr dot fr is equal to 0. Now you go in the integral this thing equation. dr dot del cross f of r. Okay. The Stokes theorem. dr dot f
Yeah.
ds dot del cross fr. So dr dot f of r requires dr dot f of r is equal to 0 requires ds dot del cross f of r is equal to 0. How can that be 0 if this is not 0 everywhere?
This is.
That is the question. Okay. Now you are saying that I have to, okay, so I have to satisfy this condition at the same time the condition. So one way is to answer your question is probably there is no periodic orbit in standard curl forces, okay, which are non-Hamiltonian. Okay. Now the other possibility you can think about is that this condition can be satisfied simultaneously with this condition only if the two areas, either it goes and it comes back to itself, or you have this kind of, there is a kind of cancellation of the area.
Okay. So it's like a projection of
one big
whole thing.
and the other becomes negative sign. Okay. Yeah, I think I've written here. Surface gives equal number of positive and negative contribution to surface integral. This is actually discussed in more detail. So it is very valid, but this is what. So coming back to this is it's velocity. I mean, it will be deterministic problem that at a given point the velocity will take two values. Actually, it is not true. Correct.
Okay.
It comes back to itself.
Okay. Thank you.
So, any other questions?
I have to leave. I have to leave now, so I hope you can excuse me.
Yeah.
Thank you.
I'm about to wind up. Yes.
Thank you.
Yeah.
Bye.
Any other question from student side? Okay. If not, let us conclude this session.
Hand raised.
Yeah. Yeah. You want to say something?
No, sorry. I didn't know that this hand was.
Okay. Thank you for accepting our invitation and delivering a very interesting lecture in this series, madam. Actually, I have observed that this is a very longer, extended version of your talk, which you have given in the conferences. I enjoyed it. Yeah. A quick note before concluding the session. We have put most of the lectures in our department YouTube channel. The link is given in our department homepage. Please visit the homepage and visit the channel and enjoy the lectures.
I just hope that, I mean, some of your students and Professor Lakshmanan's student will take up this topic. Even Professor Lakshmanan actually can, I mean, look at this topic in more detail, and he has such expertise on this topic that he can actually give us new directions and new ideas about it. So, Professor Lakshmanan, I mean, you please let us know, I mean, let me know if you have any new ideas, new questions. Ambika, to you too. I mean, your question was very good and yes, very pertinent. So if you come up with any more questions like this, please let me know.
Okay, thank you.
Good. Professor Lakshmanan, I look forward. So I'm not going to let you go. I have chosen this topic especially for your.
Yeah, sure. I will look into it.
Thank you.
Okay, then. Bye.
Bye.
Bye, Professor Lakshman. Bye.
Bye.
I will write to you the other things.